Okay, so we'll start in on motor controls, and really this unit is on taking industrial controls and applying them specifically to how we turn motors on and off. And we can either do that all the way on, all the way off, or we can gradually spin up and spin down. And so we're going to go through some different techniques and different technologies that we can use to control motors. Primarily, it's going to focus on an on-off with a motor contactor overloads as a motor starter, but we're also going to talk a little bit about soft starts, which is that gradual on to off, and then also VFDs, which we've worked with in the lab, variable frequency drives, basically varying the frequency of our motor to vary the speed. And that's the most efficient way to control a motor, actually the most energy efficient as well. So walking through an overview of this week, we're going to talk some big picture things. We're going to look at motor circuits specifically, of course, the starting methods that I just alluded to, different drive types, and then control versus power diagrams, the schematics of how we represent the different parts of the circuit now, and then control circuits, specifically motor starter, start-stop stations, and interlocks. And we'll take a video for each of these sections of our slide presentation. So first, the goals of this week: design and implement common industrial control logic to control electric motors. So we're going to extend our industrial control logic conversation specific to motors. We're going to also implement industrial safety devices, specifically motor overloads, to protect the current of the motor and ultimately protect the motor itself as it senses an overcurrent scenario. And then we're going to look at understanding the differences between control circuits and motor power circuits, kind of the pros and cons and why we have both. And then practicing designing, drawing, and evaluating motor control circuits. It's going to be a combination of in-class assignments, the multi-sim with the lab as well, along with some of my demonstrations. And so again, if we kind of pull out, look at the whole course as a whole, initially we started with, and we have 3 learning outcomes for this course that will understand that human and equipment safety are essential elements of effective electrical systems, and that effective solutions to electrical systems require understanding relationships between variables of current, voltage, resistance, inductance, capacitance, impedance, power, and energy. And so, and of course we have our troubleshooting one as well, but really this week we're talking about the human and equipment safety and their relationships. So just a quick review. Last week we talked about industrial controls and we started the conversation of relays. And a relay was a system that has a coil and a contact. And when you energize the coil, it changes the state of the contact. It basically changes whether that contact is open or closed. A contactor is a big relay. It's a higher power rating device, and it has more connections or contacts, more switching contacts than a relay. A relay usually has 1 to 2. A contactor actually has 3 to 4. And so again, it has the coil, but it now has contacts, and it has anywhere from 3 to 4 sets of contacts. And really this is for controlling high power loads like a motor. And so the current rating on these contactors anywhere from 10 amps and higher to handle the current draw from our motor. And so just like we had a control relay, we now have a contactor, and my coil is here. So I have my coil, and that's just an electromagnet. And so when I have 120 volts and I come off of 120 volts with a switch, and I'll say a push button, and I connect to the coil, and then the coil to 0 volts. And if I press down on that switch, I now have a closed circuit and current can flow through the relay coil. And this is now a magnet, and it sucks that armature down and it changes the state of these contacts. And this is just a single contact, but we can envision 3 of these as a ganged contact, or 4. And so for our motor, we have either a normally closed on this side. So if I looked at normally closed, I have my common, and then normally open. And this is really representing, so this here can be represented as normally a common in the middle, servicing a normally open and a normally closed contact. And when the coil is energized, of course, I switch to now closing the top and opening the bottom. Okay, but of course, normal state is when it's de-energized, when it's sitting on the shelf, no power energizing it. It's the state that it is out of the box. And so if we envision 3 of these, and normally we usually don't have the normally closed on the contactor, because really all the contactor primarily purpose is to do is to turn the motor on and off. So we just have a normally open set of contacts, and they all close to close all phases of the motor. If we look at a single phase motor, and we can envision this as a single phase, we would be connecting, I'll kind of get rid of this so we can see the electrical connections. We would be saying, let's say this is, again, a 120. We can have it be a 120, it could be a 240. Because I'm showing one contact, we'll just keep it a 120. And so I could be coming off of my 120 through my common, and then out of my normally open into the motor. And then the motor then could be going back to 0 volts, right? That could be our neutral. And so when I close this push button 1, the coil of contactor 1 is energized. I close the contact associated to that contactor, and it energizes the motor. It allows current to flow from my 120 volt power source down through my motor. And so now current can pass through here to my motor, back to the neutral bar, and of course I have a spinning motor now, as long as I have my push button touching, push down, and my coil is energized. Okay, so that's all review of relays, but really extending that to now multiple switches or contacts, as we call them now, inside of a relay or a contactor closing for a motor, because we have more phases to deal with. And the other big thing is contactors for high power things. You can actually use a contactor for lighting circuits as well. Lights in our lab and Sukup actually are high power. There's a lot of lights, and if you especially go down one of the hallways, there's a whole lot of lights down the hallway. You're going to have a lighting contactor as well. Have a little itty bitty switch that you push, low voltage, low current, controls a big power load, whether it's a motor, it's a whole rack of lights. And again, the symbols, we started getting this in the previous page. For a contactor now, we have our coil. We have our contacts. And these are normally open. That's a normally open representation. We can draw NO and .O, however we want to do that, but really that image is also representing a normally open, and that's the image that we would use, the symbol we would use on our circuits. And then of course, this is the pictorial here. I actually would have something that would be inside here as my contacts, 3 separate. For my L1, L2, L3, this would go to the motor. And then I would come from wherever I have my 40, 480, 208, whatever the voltage is, 3-phase. There's actually another contact usually as well, a 4th contact, and we call this an aux contact, auxiliary contact. It opens and closes with the 3 for the motor power, and it's normally used, commonly used, to sense when that contactor is closed or when the motor is on. And so we'll get into this, and this is oftentimes used for memory to allow us to remember when the motor is on, or to identify when the motor is on and then remember. Okay, so it's a fourth contact that just operates in tandem with the three main contacts for the power. And the coil here is inside, it's actually inside the bottom base of our contactor. And if we watch the video this week for a contactor, they open it up and they show an animation in a real live of the inside internal workings and components of a contactor. So that relay coil, that contactor coil, resides inside kind of the base, and it allows that electromagnet to suck down contacts to close those contacts. So again, just some review from the industrial controls, extending now to motor controls, specifically contactors. Contactors are the primary on-off switch that we use to turn motors on and off. Not the most efficient, but a very, very common, historically the most common. We're going to get now into a couple other sections where we talk about different techniques for turning motors on and off, and then the logic circuits and the power circuits that we use to describe our motor systems.